Okay, so we're almost at the end of the bonding unit. We've got this lesson and one more lesson on intermolecular forces and then a review lesson. So today we're going to talk about how to draw Lewis structures for covalent compounds. We've already done that for ionic compounds. And then we have to talk about covalent compounds because they're broken down into two further subcategories called polar and nonpolar covalent compounds. So that's the focus of what we're going to talk about today. So Lewis diagrams. We're going to write element symbols and draw their valence electrons. If there are more than two atoms, we're going to place the least electronegative atom in the center. So that's really important. Example of water. What we know is that H has one valence electron, and we know that oxygen has 6 valence electrons. And what can happen very nicely is this electron is going to come over here and share with oxygen, and then we can bring in another H because it says H2, and this electron can share very nicely right here. So when we're all done and everybody's happy and they're sharing, what we wind up with is this. Now, we don't use brackets in charge because they're sharing. It's not like one is giving to another, so there's no brackets, there's no charge. But what happens is that this is not an even sharing. And we're going to talk about that a little bit, but what I want to point out to you is that oxygen has an electronegativity of 4.0, while hydrogen has an electronegativity of 2.2. So it's like me sharing a Twizzler, but I'm not sharing fairly. I'm taking 3/4 of it and giving 1/4 to someone else. So the oxygen is pulling these electrons that it's sharing with hydrogen closer to it. I also talked to you about this early on. We could draw either a dash or a line between the elements, connecting all lone electrons, and your goal is to pair up all unpaired electrons. So what I could do is, using the example of water, is where they were sharing, and I'm going to redraw this here so you can see it. Let me just quickly redraw. Okay, so where these guys are sharing, I'm going to replace that with a line like that. And then where these guys are sharing, I'm going to replace that with a line. And then what I'm going to leave is these lone pairs that are just there, but they're not sharing with anybody. Now oxygen's happy because it's got 2, 4. This represents 2, so 6, and this represents 2, so 8. Oxygen's happy because it's got 8. And hydrogen's happy because it only wants 2, so it's sharing these two right here. One dash or line is called a single bond. And I went over this with you. So here, if we look, the number of electrons being shared between carbons, so that's right here, is going to be 2. The number of electron pairs being shared between carbons, electron pairs, so this represents 2 electrons or 1 pair, because a pair is 2, so that would be 1. Two dashed lines is called a double bond. So in this case, these guys are sharing 2 and 2 is 4 electrons, and that represents 2 pair. And 3 dashed lines is called a triple bond. So right here, that's a triple bond. So that's 2, 4, 6 electrons or 3 pair. Now, we will use single, double, and triple bonds in covalent compounds because, remember, everybody still wants to achieve 8. 8 is great. So if there aren't enough electrons to make all single bonds and make everybody happy, then we can double up on electrons and create double bonds or triple bonds to make everybody happy. So let's draw HCl. So we have H with 1 and we have Cl with 7. So we can see that this is going to come over here and share. So when we do that, we wind up with this. And then we can take this pair and replace it with a bond line if we want, and just leave the lone pairs like that. There you go. Now, if they ask for a complete Lewis dot diagram, you're going to want to do it like this. This is a complete Lewis dot diagram. If they don't specify, then you can do the one on the right. Let's look at N. N's got 5 valence electrons, and then I have a second N with 5 valence electrons. Well, this N wants 3 to be happy, and this N wants 3 to be happy. So remember, I've got a total of 2, 4, 5 plus 5, so I have to wind up with a total of 10 electrons. Just like here, I had 7 and 1 is 8. 2, 4, 6, 8. I wound up with 8 electrons. You have to start with, whatever you start with, you have to finish with. So if there's only 2 elements involved and it needs 3 bonds, then this has to be via a triple bond. So what's going to happen is these electrons are going to move around. So this is 2, 4, 6, 8, 10. So when we look at this N is happy right here because it's got 2, 4, 6, 8. And this N is happy because it's got 2, 4, 6, 8, because they're sharing the 6 in the middle. So this is a triple bond. There's my triple bond, 2, 4, 6, 8, 10. I have what I started with. Okay, let's do another one. Carbon's got 4 valence electrons, and chlorine's got 7. So you can see that this is going to come over here and share with this chlorine. But I've got a total of 4 chlorines. So I'm going to bring 4 in, 1 on each side. So I'm going to give myself a little bit more room to do this. I'm going to do it over here. 1, 2, 3, 4. In comes this chlorine. 2, 4, 6, 7. 2, 4, 6, 7. 2, 4, 6, 7. 2, 4, 6, 7. That's what that looks like. This chlorine's happy, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Carbon's happy in the middle, 2, 4, 6, 8. Everybody's happy, 8 is great. Now I can replace those that are being shared with bond lines, and then I just have to put the unpaired 6 around each one. And if I count them all up, this had 4, right? I had plus 7 valence, but there were 4. So 7 times 4 is 28, plus 4 is a total of 32 electrons. And what do I have here? 2, 4, 6, 8. 8 times 4, 32 electrons. I have exactly what I started with. All right, let's look at NH3. N has 5, and H has got 1. So that's going to share right here, but there's 3 of them. So I've got 5 for the N plus 3 H's times 1 valence electron. So that's going to be a total of 8 electrons. So that's going to be N, an H here, an H here, and an H here. I can replace the ones that are shared with bond lines. And my lone pair. 2, 4, 6, 8. Exactly what I started with. Hopefully you're getting the idea of this. Okay, let's talk about the difference between polar and nonpolar. So what do we have here? A molecule is a covalently bonded substance. Always 2 or more nonmetals bonded together. Molecular compound equals covalent compound, and I told you that those two words are synonymous. So when I talk about a polar molecule, I'm talking about something that has pull. Okay? One element has a higher electronegativity than another element. These molecules are usually asymmetrical. There is unequal sharing of electrons. Okay, sharing that Twizzler, I've got 3/4, you've got 1/4. I'm sharing, but I'm not sharing fairly. It doesn't pass the mirror test. What that means is you can't fold the molecule in half to reflect itself. It's going to be different. So you've got 2 atoms with different elements and different electronegativities. Or you might have more than 2 atoms, which means that you're going to have unbonded electrons or lone pairs. Lone pairs are those non-bonded pairs. Lone pairs is also non-bonded pairs, like in the water, around the central atom. So let's look at some polar molecules. Let's look at HCl. So this represents the mirror test, right? I've got H and Cl. I cannot fold this in half, and it cannot reflect itself. If I look up the electronegativity, H is 2.2 and chlorine is 3.2. So this pair is being shared, but chlorine is pulling it toward it. So we say that this has a dipole moment. And what I mean by that, di means 2. So it has 2 poles. This side is going to be slightly negative because the chlorine is pulling this pair that it's sharing more toward it. This side is going to be slightly positive. Remember, the head of the arrow goes toward the negative side. This is the direction of the pull. The pull is in this direction. And the tail, which looks like a plus sign, is because it mimics this plus sign. If I were to take the electronegativity difference between these two numbers, the ED is equal to 1. So that also tells us that it's covalent or polar. In the next one, H2O, which we've already looked at, we're going to see how this is polar. we've got oxygen with its 6. Hydrogen comes in here with 1, and the other hydrogen comes in here with 1. Oxygen has an electronegativity of 3.4, and hydrogen is 2.2. So these pair right here, both pairs, one with this H, one with this H, are being shared, but not fairly. Oxygen has a higher electronegativity. It's going to pull those pairs in this direction. This is going to be the slightly negative end. This is going to be the slightly positive end. And there's my tail. If I look at the electronegativity difference, 3.4 minus 2.1 is going to be equal to, oops, this should be 2.2. I made a mistake, sorry about that. Is going to be 1.2, which also tells us that it's covalent. Normally anything less than 1.7 is covalent. There are some exceptions. So that's what we mean by polar. There is pole, two different elements. One element has a higher electronegativity than the other. The one with the higher electronegativity is going to be where your slightly negative charge is. Nonpolar molecules, meaning no pull. So we have nonpolar covalent, and these are symmetrical molecules. They are symmetrical. There is equal sharing of electrons or it does pass the mirror test. It can be folded in half to reflect itself. Usually we have two atoms with the same element or electronegativities. So this is like Brinkelhoff, BRINCLHOF. These are all nonpolar covalent because it would be Br2, I2, N2. Fold them in half and they reflect itself. Their electronegativity difference would be 0. We can also have more than two atoms where you have no unbonded electrons or lone pairs around the central atom. Now, there's another way that I can be, and I want you to add this. You can be nonpolar by symmetry with polar bonds. And I want you to put some examples here and we're going to talk about them. CH4, CCl4, CO2. Those are the most popular examples. And let me show you what I mean by that. Okay, so let's start with easy. So this is going to be Cl2. 1, 2, 3, 4, 5, 6, 7. In comes another Cl. So here it's nonpolar. Why? Because it's symmetrical. And this has non-polar bonds, and that's because the electronegativity difference is going to be equal to 0. There's no pull. They're sharing equally. CO2 is extremely important. This one is always on the reagents, and it's the one they love to test you the most with. This is complicated because it's nonpolar, because it's symmetrical. However, it has polar bonds, and I'm going to explain that. The other thing that makes it a little bit more difficult is because it's going to have a double bond. So when we look at this, we have C and we have O with 6. Now this O needs 2. So you can see that this one could come down here, and then this could slide over here and share. And then this one could slide up here, and another O could come in, and they could share. So if I do that, what I'm going to be left with is this. Now there's a problem here, and I'm going to show you what the problem is. This oxygen's happy. 2, 4, 6, 8. This oxygen's happy. 2, 4, 6, 8. However, if you look at the carbon is not happy. It only has 4. So what has to happen here? Well, oxygen's going to reposition 2 of its electrons. These 2 and these 2, and it doesn't matter which 2 I grab, are going to come over here, and we're going to create a double bond. So I'm going to do this in steps. What this would look like next is you've got here the 4 from the carbon, and then here's 2 from oxygen, which leaves only 2 pair left. And then here's the other 2 from this oxygen, which leaves only 2 pair left. But in doing that, this oxygen is happy, 2, 4, 6, 8. This oxygen is happy, 2, 4, 6, 8. And the carbon is now happy, 2, 4, 6, 8. We can rewrite this like this. That's a double bond, that's a double bond. This represents 2, 4 electrons, 2, 4. This represents 2, 4 electrons, 2, 4. In comes an O, those are the remaining, and here comes the other O, and those are remaining. Now let's just double check that I did this right. This oxygen's got 6 valence electrons, this oxygen's got 6 valence electrons, and the carbon's got 4. So that's 10, 16 total. 2, 4, 6, 8, 10, 12, 14, 16. I have 16 electrons, everybody's happy. The oxygen has a higher electronegativity than the carbon, and it's pulling this way. And this oxygen is pulling this way. So the pull is equal and opposite. There is equal sharing, so it is nonpolar. It is also symmetrical. However, if I were to look at the individual bond between the C and the O, the C is 2.6 electronegativity. The O is 3.4. So this individual bond right here has an electronegativity difference equal to 0.6. Oh, sorry, 0.8. Can't do math. 0.8. So this bond is polar, and as is this bond is polar. But the overall molecule is nonpolar because it's symmetrical and there's equal and opposite pole. This is called nonpolar by symmetry. Let's look at another one. CCl4. We drew this earlier. You've got C. So carbon's got 4 plus, you've got 4 Cl's times 7. So it's a total of 32. So here's this Cl. Here's this Cl. Here's this one. And here's this one. So Cl is 3.2. So you've got your Cl's pulling this way, this way, this way, and this way on these electrons that are sharing right here. The pull is equal and opposite because each Cl is pulling with 3.2. So they cancel each other out. Okay? However, if you look at an individual bond, C is 2.6. So the difference between a C-Cl bond, the electronegativity difference is 0.6. So this bond right here is polar, as is this, as is this, as is this. But the overall molecule is nonpolar because the pole is equal and opposite. So, as I said, beware, there are often polar bonds, which I just showed you, inside nonpolar molecules. And that's this one and this one. This was truly nonpolar throughout, nonpolar bonds, nonpolar molecule, because it was a Brinkelhoff. Okay, that ends tonight's lesson. We've got one more in the unit and then a review lesson.